So, welcome back to the 9th lecture of our course. And in the morning, I've presented you the tool Cantera and how we can use it for calculation of ignition delay time. And in this session, we will continue. But before this, I want just to give you a short reminder. You have an excellent tool here. You can calculate everything without much problems, but always be skeptical. So the difference between good students and bad students is, do they ask, is it correct what I see or not? So the typical student which comes in my office says, here, this is my results. And when I ask, is it correct? Of course, it was calculated. So it has to be correct. The mathematical tool maybe has calculated something, but you don't know if it's correct. You could use wrong initial conditions. You could use wrong mechanism, which is maybe optimized for 1 bar and laminar velocity, but you want to calculate an ignition delay time at 40 bar, and so on and so on and so on. There can be so many errors, and you always have to double check. Here, just an example. We increase ammonia from 0.5 to 1.5. We increase the equivalence ratio, we increase the amount of ammonia. Nevertheless, NO decreases. So, of course, then we checked literature, and then we found out, okay, this is something we can expect. But the normal student comes with this plot in my room, and I ask him, does it make sense? And when the answer is, of course, it was calculated, so the computer has done it, this is not the correct answer. Check it, check it, check it. That's always impossible. You get so much data with these tools, but do not just rely on the output. Make always a double check. Otherwise, you produce just rubbish. You cannot use it. When we go to the laminar burning velocity, so in the morning we have had batch reactor, 0D configuration. Here we have a 1D configuration. So we have a flow from left to the right, and so we have cold unburnt mixture on the left hand side, and then we have the reaction zone, and then we have the hot exhaust gas. So, and this can be used to calculate the laminar burning velocity, LBV. The idea is, if you, for example, want to keep the flame at a fixed position, and your flow velocity is faster than the flame velocity, your flame will move to the right. If your flow velocity is slower, it will go to the left. So your inflow velocity has to have the proper value that your flame stays at a constant position. And this is your laminar burning velocity. So the velocity of the cold unburnt mixture, which is necessary to have a fixed flame position, this is the laminar burning velocity following this example here. So it's a one-dimensional system we have to consider. So we have one coordinate, and we are interested in a stationary solution. So we can, of course, keep these values here. The temporal derivatives are normally 0. There are different solvers. So you can use stationary solvers, but there are also instationary solvers. So at the end, your result won't change. You get a stationary solution. So there are different possibilities to realize it. So I show here a set of differential equation for an instationary solver. So we have to consider mass flow again. Here we have energy equation as a function of temperature again. And here we have this solution or the equations for the different species we have to consider. So this is the equation system which is behind our one-dimensional problem here. Unburned mixture, flame zone, exhaust gas. And here you see some of the variables Professor Sahu has discussed in the morning. So CP, for example, heat capacity, we need it already for the homogeneous mixture. So enthalpy, heat capacity, entropy. But here we have in addition a diffusion flux, and here we have heat conduction. So we also need some molecular transport parameters to describe the heat conduction and the diffusion properly. So we have a multi-component system. This was explained by Professor Sahu in the morning. So we need some more data than today, and we need, of course, a different setup. So again, I will start with an example you can find here. So how to calculate the laminar burning velocity, simulating a freely propagating adiabatic 1D flame using Cantera. So of course, what we need to know, we need to know the density and the temperature at the inlet condition. So mixture composition, pressure, temperature, again, we need to know. So pressure is constant all over the regime, and so temperature changes, density changes, of course, and velocity changes, because finally velocity times density is constant for our system. So if we decrease the density due to the combustion process, we then have to increase the burning velocity, the flow velocity. So, and here we can use a specific class from Cantera, so Cantera.freeFlame, and so this is a model for this laminar flame speed, and we need some specific input parameters again. We need to know the temperature of the unburned gas mixture. We need to know the pressure, of course, and the composition. So to define our inlet conditions. And then we need to have a proper chemical model. And another point is the domain length. So we have a one-dimensional flame, and the flame front has maybe a length of tenths of a millimeter if we have very fast combustion process, but it can also extend some centimeters for very slow flames. So the length of your computational domain has to match here more or less. No? Should not be too long, not too short. So, and then of course we have quite some simple commands to compute the laminar flame speed. So again, we need to load some libraries here. We here have some parameters for our plotting. And then we define inlet temperature and pressure of our system. So nearly ambient condition, 300 Kelvin and 1.013 bar. We have now this well-known GRI mechanism, which we use again as an WAML file. And for this example, we have stoichiometric methane air flame, so 9.5% methane in air. So again, simply calculated using this function here, set equivalence ratio for 1 for methane in air. Here we have the flame domain, so it's 14 centimeters, for example. This number is not so important, but it should be checked. And you should not use 4 meters here when you have a very fast flame. You should not use 1 millimeter here if you have a slow flame. Better double check. Look at the results, not only at the value of the flame velocity you yield. Look at the profiles too. Double check. Always double check. Then here we call already the solver. Okay, here we have some parameters for the solver, and at the end we get our flame velocity. That's it. Quite simple, not much more complex than the example we have seen in the morning. And here we get a typical result. The temperature now is a function of distance. So cold unburnt mixture, and after a given distance we reach the flame front, and here combustion takes place, and finally we get the exhaust gas here with the adiabatic flame temperature. So, and we can then also plot species, here just the comments from the examples. So then we have here methane as an adduct, and the products water and carbon dioxide, which are normally not so interesting. More interesting are the intermediate species, H, OH, and so on, which then normally have, so H, for example, here in the region of the flame front, the maximum. So what we add here is also a sensitivity analysis. So we have discussed it already in the morning. When we change our reaction rates for each of our elementary reactions and do the calculations again. So we take equation number 1, change it by a specific factor, and calculate again, here for this example, the flame velocity, and compare the disturbed solution with the undisturbed solution. This we do for each of our reactions. So this is then explained here. So we have for MN range, that means for all the reactions we have, first reset them to the original value, and for each M just add a small quantity to your reaction rate. This here change it just by a small quantity, and again calculate the flame velocity, and then here the flame velocity is defined as flame velocity disturbed minus flame velocity undisturbed over the undisturbed flame velocity times the value of the perturbation we have performed. So again, we have something like a normalized sensitivity we see here, and we can directly see which reactions are important and which are not. So and here the outcome, again my favorite is here, H plus O2 gives O2 plus OH. So if we increase the reaction rate of this equation, we would increase the flame velocity. And so the flame velocity strongly depends on these reactions, and so on. And again, we only plot the 12 or whatever, the 12 most important reactions from over 100 reactions. These 12 are very important concerning calculation of a laminar burning velocity. So again, here we have to focus. If we know them very well, then the result can be very good. Again, we have done this first to get confident with Cantera and to check is everything working properly. Compare your tool always with literature, always with tutorials to check if everything is fine. So and then we go back to the original problem we have had. We want to analyze ammonia air, ammonia hydrogen mixtures. Okay, in this case, of course, it's not the initial delay time, it's the laminar burning velocity. We have done it for a range of equivalence ratios, and we have done it for a range of pressures. And for one initial temperature and for one specific mechanism, because in this paper here, they have also given their results concerning measurement and simulation of laminar burning velocities, so we can compare our results first with their results before we modify the initial conditions to examine our specific problem. And so this is the outcome. So here we see laminar burning velocity as a function of equivalence ratio at 1 bar and 473 Kelvin. And what we see, okay, near the stoichiometric composition, we yield the maximum velocity, something we can expect. And if we increase the amount of hydrogen, the flame velocity increases. Also something we can expect. So this is this example here. Maybe can we have a short break with the video? Because I have to upload another file. Yeah? Do you have any questions concerning the presentation I've shown you here? Okay, so I've presented you now some results of the ignition of ammonia hydrogen mixtures. And of course the question is why? Why is this of interest? And so I present you some results we have presented at the ammonia symposium. I think it was the first one in Bristol, where we have, and just close it, can close it, thank you. Where we first have discussed the dependency or the parameters we have to consider when we want to examine ammonia hydrogen air mixture ignition by electrical discharges, by classical electrical sparks. So when we look at such a typical spark, normally concerning safety issues, for example, we focus only on the energy. So hydrogen has a minimum ignition energy of 17 microjoule, so a very, very low value, so it's very difficult to handle. Propane has a minimum ignition energy of 420 microjoule, so much safer to handle. And when we go to ammonia, we have an ignition energy, minimum ignition energy of 15 millijoule. So nearly 3 orders of magnitude more energy is necessary to ignite ammonia compared to a hydrogen air mixture. But of course, the energy value you can find in literature is always based on the energy stored in a capacitor. So it's the breakthrough voltage times squared times 0.5 times the capacitance of the capacitor. So we have just an energy value, but we don't know anything about the plasma we see here, and we don't know anything about the combustion processes and ignition processes leading to a self-sustaining flame propagation. So when you look at these numbers you have, 17 microjoule hydrogen, 15 millijoule ammonia, you always have to consider that these represents values where we have in 1 of 100 cases an ignition. So we are really at the border between ignition and no ignition, but this is not a sharp border. It's of course a statistical process too. So here, I think this is it's for propane, the example. We have several experiments here, and you have can find a boundary between ignition and no ignition cases, but of course it strongly depends on the experimental configuration. So this is important if you compare results from literature. It always depends on the type of experiment which was performed. And so here, for example, you see the probability of ignition near the minimum ignition energy. So 1 of 100 experiments should ignite. So the minimum ignition energy is somewhere here. So it is clear that there is, of course, also a large error on this number. So when we look at typical spark, okay, here we have the electrical energy. This we know, we can measure. But of course we have external circuit losses, which we may not know, and we have the spark discharge. So not all of the energy is not distributed to the spark discharge. Then we have a formation of the spark channel, and we have losses due to electromagnetic radiation, and we have cooling at the electrodes. Again, some joules are lost. Then we will have a shock wave, which leaves our spark channel at a given time. First of all, some energy is then distributed to the surrounding again, and the spark channel itself is broadening from several micrometer up to several hundred micrometers. Then the question is, okay, which energy is applicable for the ignition process? And this is what we can vary, and the rest we have to examine. So from literature we know for hydrogen a lot. So hydrogen is examined very well. So we know the minimum ignition energy is 17 microjoule when we have a gap distance of 0.5 millimeters. So this we know from literature. This was repeated very often. For ammonia in air, you cannot find so much data because it was not of interest very long. So you can find results here, 14 millijoule, but you can also find 680 millijoule. Again, it depends strongly on the method you use. And here we have a result of work at PTB, where we have varied the electrodes and the spark gap. And you see here, when we have a gap of 50 millimeters, we get our minimum value. At nearly stoichiometric conditions, so phi equals 0.9, there we get the minimum value. It's 14 millijoule compared to 17 microjoule. So big difference, and we have had 0.5 millimeters for hydrogen in air, and here we have 15 millimeters. So this is the optimum gap distance. So then now the question is, if we want to use in the future ammonia-hydrogen air mixture for different applications, how will we have to consider this minimum ignition energy as a function of hydrogen composition? Because this is an important factor if we want to consider safety aspects. So how can we simulate it? This is an extension of the tools I have shown you in the morning. So here we use a classical spark. So here we have an 1D configuration again, and that's a cylindrical configuration. That means we have gradients only in this dimension, in R direction, and no changes in this direction. So again, we can use in one-dimensional configuration to represent our ignition problem. So we deposit energy here, and then we calculate ignition and flame propagation perpendicular to this spark channel. But we also have calculated laminar burning velocities, and we can also calculate extinction strain rates if we want. So we have a lot of different tools to examine the system in total. And if we talk about minimum ignition energy, this is the quantity we need to know. But when we look at the energy equation, you cannot find the ignition energy alone. It's always a quantity of density, because your energy is deposited into a specific volume. And as said before, the spark gap concerning ammonia is 30 times larger than the spark gap for hydrogen. So when we put now this number, so nearly a quantity, 3 orders of magnitude larger energy, okay, but this we can already divide by a factor of 30 concerning the energy density, because we deposit, in case of ammonia, the energy in a much larger volume. So this we have to consider here. And then, of course, the initial radius of the spark is of importance. So first, we have used a specific mechanism optimized at PTB from colleagues to perform the simulations, and we have used this mechanism, have compared our results with literature. So here we have the flame velocity, so 6.5 centimeters per second for ammonia, and 2.3 meters per second for hydrogen. So quite confident comparison with literature. Here we have the extinction rate using a counterflow configuration. Again, our simulations at 5 different pressures compared with literature, sufficient result. And finally, here we have the ignition delay time. Oops. As a function of amount of hydrogen, which then reduces here drastically and again compared to literature. So we were confident our numerical tools are working properly. So the mechanism was implemented correctly, and the set of equations we are solving were solved properly. So here we can define the spark. We use a specific profile here. There you can use, so this is a factor of 8 we see here. Of course, you can use a square or linear relation. So in this energy, in this volume, the energy is deposited. And of course, the radius here is of importance. So we have varied the energy in the range of 70 microjoules to 40 millijoules. The spark length was in the range of 3 millimeters to 50 millimeters. And we used different radiuses here to examine the process, and also we varied the energy deposition time for always phi equal 1 mixtures at initially ambient conditions. So what was the outcome? So here you can see the flame front as a function of time. So in case of ammonia, pure ammonia, you see a very slow flame propagation. In case of hydrogen, we have a very fast flame propagation. And so, as expected, increasing the amount of hydrogen, the flame velocity increases. Here you see the amount of hydrogen atom as a function of time again. So you can see pure hydrogen ignites very fast, and here pure ammonia ignites very late for this specific configuration we have examined. So there was an assumption that in case of hydrogen we have something so-called preferential diffusion. So hydrogen is a very small molecule, so it diffuses very fast. And preferential diffusion means that you no longer have a homogeneous mixture. So if you have a temperature profile, the hydrogen is moving faster to the hot zone than the ammonia. And so you have something like a hydrogen enrichment in your flame front. So this we can examine numerically. Lewis number equal 1 means all species have the same diffusion velocity. So there is no preferential diffusion, of course. Then we can say it's only for molecules smaller 15. So this is not correct here. Mole mass of smaller 15 gram per mole, and thermal diffusion for all species. And you can see an effect here but this is after the ignition. So we can see here an influence of this thermal diffusion. So the hydrogen is enriched at a specific condition. We see here the maximum amount of hydrogen in our system, but the ignition takes place more or less at the same time. So this has no influence on the ignition process itself, or no significant influence. So then we looked at the radial profiles of selected species. So here we have the temperature profile. So we have a rich ammonia hydrogen mixture. Rich means we have 80% ammonia, 20% hydrogen. And here we have the temporal development of temperature. So at the beginning, of course, 300 K. And then we deposit some energy. It heats up, and then the flame front moves away from the hot spark channel into the unburned gas mixture. And the length of the energy deposition is 100 microseconds. So after 100 microseconds, the flame velocity, the temperature decreases again inside the hot gas kernel, but here combustion has taken place, so the flame moves to the outer side. This we also can see when we look at this hydrogen, for example, or even better here in case of the H atoms. I don't know why we have such an unusual plot here. But again, so this increases drastically in the hot region, and then after the end of the energy deposition, it decreases. And what is interesting concerning ammonia, so we have talked about OH and H for the hydrocarbons and hydrogen as a flame front marker. For ammonia, NH2 is a better flame front marker because the other radicals are consumed. We cannot see them so much. So here, when we look at the H profile, okay, we see where it is hot, where the energy deposition is, but we cannot see the flame front. But here we see it for NH2 very clearly. So here we see the outward propagating flame front. So only in the flame front we have some NH2, and in the cold and hot region nearly no NH2. So what is the big difference? So we have seen we have a much longer ignition delay time for the ammonia for this configuration. And so here we have again very rich ammonia mixture, 95% and only 5% hydrogen. And we vary the energy here, so 0.6 joule per meter, clearly just fast ignition. So then temperature here is dominated by the energy we deposit from the spark. And then here we have the adiabatic flame temperature, more or less, we see. If we use 0.5, we heat it up, and then no ignition takes place, the system cools down. But we also see here some interesting cases, 0.54 and 0.55 joule per meters. So here the chemistry needs some time. It's not clear, will the ignition take place or not? So here, in this case, energy was not sufficient. So no ignition takes place, it will cool down. But in this case here, it then starts to ignite. which is also very unusual compared to typical hydrocarbons. But especially for hydrogen, you would not expect such a behavior. And this is, we can also see in the chemistry here, we look at the H atom. So after end of the spark and energy deposition, we have for a very long time, we see a lot of H atoms, and at 4 milliseconds, nearly 4 milliseconds, we can see clearly differentiate between ignition and no ignition, which is very long, a very long time period. Here, this is a classical hydrogen example. Here we have 80% hydrogen, 20% ammonia, energy deposition, end of energy deposition, and then the final ignition takes place. This is classical, typical spark experiment. If the energy is not sufficient, it just cools down. And you see it more clearly here at for example, NH2 radical. In case of ignition, we produce a lot of this NH2 radical, and here we see the amount we have in the flame front. In case of no ignition, we produce nearly no NH2, and of course no ignition has taken place. So what is now the outcome concerning the minimum ignition density? So again, the difference in the minimum ignition energy is nearly a factor of 1000. 17 microjoule compared to 14 millijoule. But when we look at the density, we see, okay, we start here at this specific number, and we end here. You see it's maybe one order of magnitude. So what is the difference? The length of the spark is much longer. And what we have not considered here, which I will show you later in this lecture, if we use sparks with such a high energy, they are also much broader. So in typical spark for hydrogen, we are talking of a radius of the plasma of maybe 100 micrometer. Here in case of ammonia, the energy is deposited in a channel which has a radius of nearly 1 millimeter or even more. So we have much higher energy, but we have also a much larger volume where the energy is deposited. So the energy density difference is quite small. The energy density difference is quite small when we compare ammonia with hydrogen. This is very helpful if you consider to enhance combustion processes of ammonia, for example, in combustion engines. We have to add some hydrogen to enhance the combustion process. But you see, unfortunately, the ignition process is very sensitive. So small amount of hydrogen drastically reduce the ignition energy we need. Unfortunately, the flame velocity does not change so much in this area. So when we talk about applications with maybe 20% of hydrogen, it increases, of course, the combustion process, but it's so to come in the range of hydrogen, we would need much more enrichment of hydrogen. So I have shown you a practical example of the simulations we have discussed today in the morning and in the afternoon, extended with another model which we will discuss next week in detail. And I have shown you that, of course, we have used quite simple 0D and 1D calculations. So no sophisticated 3D turbulent flame calculations, but nevertheless, using these simple tools, we can learn a lot. We can examine the important parameters, and this is, in my opinion, much faster and much more reliable than using here, for example, an open foam setup. But of course, this always depends on the application you are interested in. So with this, I'm at the end for today. Do you have any questions?
So for calculation of the laminar speed or the laminar flame velocity, so we are using the equation which is dependent on your diffusivity, reaction rate and onboard temperatures. Okay. So in experiments, so how do we calculate them? In practical sense, how do we calculate the flame speed? And what are the techniques associated?
You mean how to determine
Yes.
laminar burning velocity experimentally?
Yes.
So one possibility is to use a pipe and adjust the inflow velocity that you have a stable flame position. So then the velocity of the unburned gas mixture is your laminar burning velocity. But of course, this is quite complex. There is a concept of a heat flux burner. Here I'm not an expert how this is working. This can be used to determine laminar burning velocities. Here I have to check the details and maybe can give you this later. A much easier setup is a classical combustion vessel, like you see here. So here you see an ammonia air flame ignited by a spark, electrical spark. And you can examine the flame front propagation as a function of time in such a configuration. And with some mathematics, so you do not see here directly the laminar burning velocity. You see more or less an overall global flame velocity. So you have an expansion of the hot gas kernel, and you have, of course, a curvature effect. You have at the beginning a very small flame ball, which then increases, so the curvature reduces. But with so you can measure flame front as a function of time, and then calculate from this the laminar burning velocity.
Okay, from that conical structure to the parabolic or the radius structure.
Pardon?
Once like it happens in the Bunsen burner, so it's first remains as conical, then it's becomes.
I think you can also use something like a Bunsen burner for this, but then you of course have to consider that you may have not a flat flame. Any further questions? Okay, then we can finish for today. Thank you.
So good evening to everyone. So myself, Kiran Kumar. So I'm a postdoc fellow here, so under the mentorship of Professor Sauser. So today's my presentation is on heat transfer enhancement using metal foam and its application in combustion process. So when it comes to any heat exchanging devices, its primary objective is to enhance heat transfer performance. So that is the basic things. So when we consider any heat exchanging, and to improve its efficiency, so that is the priority, it will be there. So that leads to a creation of novel technologies as well as optimization of the current existing technologies that is required there. So in order to do that, there are different techniques or methods are available. One is enhancing the heat transfer surface area. So by that we can enhance the heat transfer. Another one is we can improve the fluid flow characteristics. By that also we can enhance heat transfer. Then the application of nanofluids, so by that also we can enhance the heat transfer performance. Then improving the design of any heat exchanging devices, so by that also. And one more method, it is the introduction of porous media in the heat exchanging devices. So my research work, it is done by using porous media. So now we will see what is this porous media it is. So porous media, it is nothing but a matrix with interconnected voids. So what we can see it in this figure left side, so the skeleton portion of this object, so that we call it as a matrix. So that is interconnected by a voids. So that path that is available for the fluid to flow, that we call it as a pores. And that skeleton portion or matrix, we can call it as a ligament, or sometimes it is also referred as fibers. So when it comes to this porous media, so there are two types. One is deformable porous media and another one is non-deformable porous media. So as we can see this example of chalk, this is comes under non-deformable porous media, and this sponge, it is comes under a deformable porous media. And based on its occurrence, so natural porous media as well as artificial porous media, it is there. So these are the few examples for natural porous media as well as artificial porous media. So our case, it is heat transfer enhancing using metal foam. So metal foam, it is artificially prepared. So for our requirement, for our specification according to our design, so we can prepare this metal foam. So that is comes under artificial porous media. And this metal foam, when it comes to this, two types are available. One is closed type, another one is open cell. So the first one, this is a closed type. So this is mainly used for energy absorption applications. So like car bumpers. So this is having a capacity to absorb impact load. Okay. So soundproofing. So for that also it can be used. And for thermal insulation purpose, so we can use this closed cell metal foams. And open cell metal foams, this is also a good energy absorb capacity, but mainly it is focused for to use it for heat exchangers to enhance the heat transfer performance. So this is having a pores, so which will allow the fluid to flow through it. So by that it will enhance the surface area. By that it will be enhanced. Heat transfer will be enhanced. So this open cell metal foam, so it is a rigid sponge made up of metal or metal alloys, and it possesses some characteristics. So like one is pore diameter. So what you can see it in that skeleton structure, the pores, the voids that is available for the fluid to flow, that we call it as a pores, and its diameter. So it is not exactly a circular shape, it will be somewhat annular shape, it will be there. So average mean diameter it will be considered, so that we call it as a pore diameter. And what you are seeing is ligament, or it is also referred as fiber. So that diameter we can measure it, so that is fiber diameter or ligament diameter. And another property, it is pore density. So what is that pore density means? It is referred by as pores per inch. So PPI, pores per inch. Per inch, how many pores are available? So as you can see it in this second figure, figure A represent 10 PPI, B 20, C 30 and D 45. So if you consider first one, that is 10 PPI, means 10 pores per inch. So if the pore density is lesser, the pore diameter will be larger. If you go by higher pore density, that is 45 cases, so the pore diameter will be lesser in cases. So this plays a major role in the heat transfer enhancement. So pore density. The next property, it is porosity. So it is calculated as a ratio of volume of pores to the total volume. So that volume of pores can be calculated as total volume minus solid volume. So divided by total volume. By that we can calculate the porosity of that particular matrix. Another property, it is permeability. So it is the ability of the metal foam to allow the fluid to flow through it. So that property we call it as a permeability. So these are some of the important characteristics that is possessed by a metal foams. So when we introduce metal foam in the heat exchanging devices, yes, of course it will enhances the heat transfer performance. So that is what we have observed in the literature also. But what is the novelty of my research work is that, yes, of course enhances the heat transfer performance, but at the same time when we introduce metal foam, it will increases the pumping power, means the pressure drop also it will increases, so that we can't neglect. So anyway, the primary object is to enhance heat transfer, but the increased pressure drop we can't neglect it. So if the pressure drop increases, we need to supply more pumping power requirement, so that is the loss, so efficiency will reduces. So we need to concentrate on that factor also. So my research work was mainly focused on that one. So to optimize this increased pressure drop with higher heat transfer rate. So in order to do that, I have used the application of second law of thermodynamics. So that is exergy and entropy generation analysis, that what I have performed. So my work is numerical work. So for that, I have considered the geometry that is similar to the experimental that is done by Kamath et al. That is in IIT Madras. Okay. So this is the geometry experimental setup whatever they have. So at the center, so they have a heater. So beside that heater, aluminum plates are placed. Then beside that one, we will have a metal foam here. So from the bottom, so air will be circulated. So there is the anemometer to check the velocity of that one fluid. So air travels from bottom to upwards. So it carries the heat from the aluminum plate. So heat will be transferred. So in order to enhance that heat transfer performance, so metal foam is introduced in the channel. So this is the numerical model. This is my work. So similar to that experimental setup, I have created one model, numerical model, a vertical channel. So you can see it at the center, we will have a heater. So in the experimental setup, what they have done is they have considered one mica sheet. On that they have wounded nichrome wire. So they have created a heater like that. So in my case, so I have considered at the center of the channel, we have a heater. So beside that, they have also placed aluminum plate. I too have a placed aluminum plate. Its size is 250 by 150 by 3 mm. Whatever the dimensions they have considered, same parameters I too considered here. So from the bottom of the channel, air will be circulated, and whatever the aluminum plate, it is received the heat from the heater. So that will be transferred to the air by convection phenomenon. Heat will be transferred. So that case we call it as a empty channel. So in order to enhance that heat transfer performance, what we have done is same case as that Kamath et al. We have introduced the aluminum plate. So aluminum metal foam. So that parameter what I have considered is 10 ppi. So its porosity that is 0.95 and its dimension that is 250 by 150 by 10 mm. So this is the top view of that one. So air flows from bottom. So whatever, because of this introduction of metal foam, the heat transfer surface area that will increases. So by that heat transfer enhances. So at the same time, as there is an obstruction to the fluid flow. So in the beginning case, empty case, there were no metal foams. So in that case, there was no obstruction. So the pumping power requirement, it was less. But now when we introduce metal foam, definitely there will be obstruction to the fluid flow. So pumping power requirement, it has to be enhanced. So pressure drop, it will be enhanced. So in order to measure the pressure drop, so pressure here, they have a pressure measuring devices, pressure taps there. So across the metal foam, they have placed it. So I too in the numerical simulation, at this location, I have measured the pressures. So pressure will increase. So we need to optimize this increased pressure of such a way that it should not exceed the heat transfer performance. So that was my work. So in their work, what they have considered is the completely filled metal foam. So whatever the channel it is there, 27 mm, that 1 mm it is heater. This is 3 mm, 3 mm, so 7 mm. So that means this one is 10 mm, this one is 10 mm. So for 10 mm, they have filled the metal foam. So in my case, what I have done is, I have considered partial filling cases. So I have taken 25% filling case. So figure A represent 25% filling, figure B represent 50% filling, and C 75% filling, and D as 100% filling. So what is the effect of partial filling over the completely filled channel? That analysis also I have performed. So this is the, as you can see it in this model. So the geometry, it is symmetrical along y-axis. So in order to reduce this computational time as well as the space that is required to store this one, so I have considered only half of the geometry. So that includes heater, one aluminum plate and one metal foam it is there. So in that, the Side wall we consider it as adiabatic wall conditions. Then air is traveling from bottom, so this is the inlet condition. So uniform velocity we have maintained. Then at the outlet we have considered atmospheric pressure or gauge pressure as 0. Then this is the heater, so uniform heat flux is provided. This is the aluminum plate and this is the metal foam we have filled it, and this we consider it as a symmetry. So here the simulation is performed by varying the velocities, different velocities like 0.1, 0.5, 1, like that we have varied the velocities. So for different cases also same boundary conditions what we have considered and we have performed. So in that it is observed that 100% filling, it gives more heat transfer. So if you use completely filled channels, yes, because of more surface area, so more heat has been transferred. But at the same time, pressure drop also it is more in case of 100% filling rate. So if you just concentrating only on the heat transfer performance, yes, 100% is the best option. But we need to consider the pressure drop also. So with the consideration of both heat transfer enhancement as well as this pressure drop, so we come to know that 75% filling gives a better result. So that is giving a good efficiency. So this is what our results it is focused. So that is one part of my work. So in the another part, once again I have considered one more experimental setup that is done by Borag et al. So the previous one is the vertical channel. Now it is the horizontal channel. So this is the test section. So there, this is a circular form. So okay, so this is the test section. It is, we can see it here. So inside that they have attached a metal foam to that pipe. Okay, so this is the entrance length and this is the exit length. So in order to validate that one, so I have also considered the same numerical model. So this is the test section. So this is 1000 mm length, 7 mm wall thickness, 100 mm diameter. So this is the metal foam that is attached to the inner wall of the pipe. So aluminum metal foam of 10 ppi and 0.95 same I have considered. So this is my numerical model. So this is the entry length, this is the exit length. So this is our test section. So they are also wounded a heater on the circumference of the pipe. So I have, in my work also I have supplied the heat, uniform heat I have provided, and they have considered completely filled. So I have to check completely filled as well as partial filling cases. So what you have presented here, one is partial filling cases. So here inlet velocity assumed to be uniform, then the outlet pressure, that is gauge pressure, we have considered it as 0, atmospheric pressure what we have maintained. So same conditions what we have considered with respect to previous one. That is one case. Then this in the another case. So in the previous case, this what we are seeing in figure A. So the metal foam, it is attached to the inner wall of the pipe. So now to check its best position, where it's going to give best thermodynamic performance. So what I have done is, so in first case I have attached the metal foam to the inner wall of the pipe. In the next case, I have inserted the metal foam at the core of the pipe, center of the pipe. So then once again that simulation is carried out. Then I have checked the performance. So from the performance it is, we come to know that, so the metal foam filling adjacent to the inner wall gives better performance compared to that of the metal foam insert at the core of the channel. The reason is that, so here from the, on the outer surfaces we are providing the heat. So as a result, so the metal foam wall that absorbs more heat and it will be transferred to the fluid. So more heat will be transferred there. At the same time, when the fluid is flowing at the, for these cases, when the fluid is flowing, so you know that the velocity it will be higher at the center of the pipe. So when there is a high velocity, more obstruction, so pressure drop will increase. So for our better performance, pressure drop should be low, heat transfer should be high. So in these cases, so pressure drop is, heat transfer is high as well as pressure drop is low. So because of that factor, we are getting a good result for first cases. In that I have also varied different thicknesses like 10 mm thickness like this one, 10 mm, 20 mm thicknesses, 40, 60 and 80 mm. So I came to conclusion that the by observing the result up to 40 mm thickness, it gives a good results. Okay, so that gives a good thermodynamic performance. So that is what my research work, and where we can use this metal foams. So we can use it for several application in engineering disciplines. So in aerospace engineering, so like in cryogenic coolers, then in electronic equipments like your CPUs, GPUs, okay, battery coolers, then in solar systems, even in medical field, MRI scanners, okay, to enhance the cooling rate, as well as in especially it is more focused on compact heat exchangers. So because the property of metal foam one is that it is having high surface to volume ratio, so it is more suitable to use it in compact heat exchangers. So radiators, so refrigerators, air conditioners, so there we can make use of it. And also we can use it in geothermal systems, so for filtration purpose also we can make use of it. Then also for solidification purpose, in order to enhance the cooling rate, so we can make use of for all these things, as well as we can use it in the combustion chamber. So if you use it in combustion chamber, what is the advantages that we are going to get it? So this is not my work, so just in link to this course, so just I have to consider this factor. So of course, if you use this metal foam, the primary objective of using the metal foam is to enhance heat transfer performance. So of course, when you introduce this metal foam in the channel combustion chamber, definitely heat transfer will enhances. So another factor, what is that? It gives flame stabilization. So that means, as you have seen this shape of this metal foam, it is having intricate shape. So when the fluid it is flowing through that one, it will create turbulence flow. It is not a laminar flow, so it will create a turbulence flow. As a result, the proper mixture of fuel and air takes places. So because of that proper mixing, so combustion, it will take places completely, almost it is completely. So the left out unburnt gases, it will be very less, so we can reduce that one. So if the unburnt gases, if it is left out is less, that indicates that so the emission of pollutants like NOx, nitrogen oxide or nitrogen dioxide, like carbon monoxide, so that emission can be reduced. So that is the advantage of using metal foam. Then as I told you, it can also be used for some specific purposes like a insulator, so where we can absorb that heat and store it, so it should not be lost the heat, so there also we can use it. And it is having a good energy absorber capacity, so for noise as well as damping coefficient, so that can vibration it can withstand and it can reliable, so for long many days. And it is a lightweight component, metal foam, so fuel efficiency, it will be a factor, so we can increase the fuel efficiency. So because of that we can use it in aerospace applications and automotive applications. So this is the one factor. And use of this metal foam in combustion process, so we can control the combustion rates. So that is as I've shown, this pore density or porosity, okay, so we can manufacture according to our requirement, like 10 ppi, 20 ppi, 45 ppi, like that. According to our requirement we can manufacture, and we can control the propagation of flames. So all these options that is available if you use this metal foam in a combustion process. So this is regarding my presentation. So these are the references, and these are the, with respect to my research work, these are the publications that I have done. So all are SCI journals, so and book chapters, then conferences where I have presented, and for the second paper I have received the best paper presentation award. So this is regarding the presentations.
I have a question.
Yeah.
Can you please specify which metal alloy has been used?
Aluminium metal. So generally metal foam is created by using different materials like aluminium, copper, zinc, titanium, all those things. So as you are aware of it, copper is a good conductor of heat. Okay. So that is also in the literature I have observed it. Copper is a good conductor. And also aluminium also in some researchers they have used. So what I came to know that, so yes, of course copper gives good result, but it is not much compared with respect to aluminium. So it is somewhat slightly improvement it is there, But yes, of course, it is a numerical study. We can use it. But when it comes to practicality, cost will be higher. We need to consider that factor also. So considering that cost factor as well as that performance, so aluminum plays a good option for me. So that's why I used aluminum.
Okay. In also in slide number 15, uh, you mentioned that that it is also good for noise and vibration damping.
Yeah.
My question is, some materials, especially metal foams, when they absorb noise and vibration and they damp, they are basically absorbing energy, and they mitigate it by managing by heat transfer as well. But in the process, they also get somewhat heated.
Yeah.
So I think that if their temperature rises, it would affect their heat transfer
No.
negatively.
No,
So heat
no.
transfer rate would decrease somehow.
See, this is metal foam. It also acts like a catalyst. So that is also one thing. So whatever that vibration damping, that can be converted into heat form also.
Yeah, that's what I'm
Ah.
saying. If it's getting converted into heat form and staying in as heat energy in the ligaments of the porous material, so that would affect the heat transfer rate, right? If the temperature
That's only, it's going to increase the heat transfer performance only.
No, I'm saying that it would decrease because the temperature difference would reduce as the temperature of the metal foam that would go up. So the temperature difference would be reduced. So the heat transfer rate would also reduce. Is what I'm trying to say.
So there will be a gases. So in combustion, so that will carry out that whatever the heat will be there in the metal form, that will be carried out by the flue gases.
Question if it is true that if you use that foam for a longer run,
Yes, sir.
Longer.
impact effect, that is the question I believe.
Yeah.
Isn't it?
Yes, sir.
How to prove? See, there are a lot of emissions with particles that comes up. So one point of time you saying that it will allow the heat transfer. But with time, if the same material getting used, they will act as a kind of a insulation for because of other particles that gets developed through this process of its use.
Yes. So this is I need to work on, sir. So this is my research work was previous one. So whatever I've shown. So this is just to relate to this course, So I have considered this topic how my metal foam can be utilized in combustion chambers also, process also. So that we need to work on.
Is that you have to think about whatever foam material, you have to do some kind of life cycle analysis.
Yeah.
Okay. You can say that you use it for this many durations. It will have good effect in transport. That may be possible. Study.
Yes, we can concentrate on that. Thank you.
Can you show your material parameters at the beginning? I think it was slide number 2 again. No, then it was where you have said you have a mean diameter which you can.
Yeah, so
Maybe.
this one.
But later, one here.
So there, so usually that pores, it is not exactly circular. Okay, so it is somewhat oval in shape. It will be like that. So average diameter. So the diameter, whatever they have measured. So in the as I've taken the study means these parameters I have taken from Kamath et al. So their experimental study. So they have yes.
From whom?
Kamath et al. So that is experimental done in IIT Madras.
Right.
So this is the
Yeah, that's okay. That's the final question. So, who is measuring these qualities? So you are not.
they have done all these parameters, sir. So they're experimentally done that work.
Yeah.
So for my research work, so their work, what they have shown is that if you introduce metal foam, it enhances heat transfer. So that is what they have presented. So my work, I have considered the same parameters and I have simulated. And what is my work is that, so yes, of course it increases heat transfer. So up to what limit we can use it?
So you have said you have a mean diameter.
Yeah, that is what.
is not sufficient, or you also need the standard deviation.
They have used the standard procedures and all those things, sir.
Yeah, but so if you don't measure it, so do you get these data? So
Yeah.
the standard deviation also from the other group?
Yeah, that is one microscope. It is there. So the standard microscope. So that name I have forgotten. So using that microscope, they are going to measure it.
So you have a mean value and
Yeah,
you
yeah.
also get a standard deviation.
Yes, sir. There is a deviations also there. So they have presented all these parameters. So that's why. So when we validated our results with the experimental results, some deviations we are going to get it because of these parameters.
Yeah.
So
So then I think it's one of the next slides where you discuss the heat transfer. Maybe one further. Yeah, here.
Yeah.
So in which dimension you are interested concerning the heat transfer? Is it the heating of the gas flow going from the
air,
bottom
the
to the
fluid,
top,
we
or
are
the heat transfer from the hot wire in the metal?
This is the heater, sir. So from the heater, the heat will be transferred to the aluminum plates.
Yeah.
So aluminum plates get heated up. So that is our metal solid surface. Okay. So we are passing air from the bottom.
Yeah.
Okay. So that air, when it comes in contact with the surfaces by convection phenomena, the heat will be carried away by
The
the.
question is which quantity is here of interest for you? The
Yes,
transfer to
the
gas
heat
flow?
transferred, that is heat carried away by the air. So that is what more interest. So if more heat is transferred, so that is good performance. If the less heat, the air, if it carries less heat, that means heat transfer is lesser. So our focus is on that one.
So you have as a flow resistance on the one hand, which
Yes,
you have
flow
to
resistance.
optimize, and you have to optimize the heat transfer to the gas phase. Then finally, concerning your burner, is it a mild combustion process? That means is the flame inside the porous structure, or is the porous structure used to laminarize the flow, and the flame is above the porous structure?
Regarding that combustion, linking to that I need to work on, sir. So that I don't have proper information regarding that. So that I need to work on. So this was my research work. So when it comes to this combustion chamber, as one case, I think we can insert the combustion chamber also. So in one figure that I have shown it. So here outside this also we can like this. We can
Yeah,
insert.
but then it's heat transport away from the combustion zone, so for cooling.
Yeah.
Yeah. Okay. So
That is also one cases that is
okay,
possible.
so
So-
you can use these structures either in laminar flame burners, as in so the gas flows from
the
bottom
bottom
to
to
top, and
top.
at the top you have a very laminarized flow, and you have the flame above the structure. But we also have mild combustion processes where the flame is inside the process.
Oh, inside. Okay.
But okay, you have a totally different application. Yeah, thank you.
Yes. Thank you.
Question.
So just go to the computational model. Okay. So you have done the 2D analysis.
Yeah. Two-dimensional we have considered. So Gambit was the software that I have used, and for simulation purpose, Ansys Fluent.
No, means what my concern is that is related to Redla also. So when you are just stacking the pole, so the poles are aligned in one direction.
Yeah.
So if you are taking a cross section and if you are putting it, that velocity in the cross sectional way, if you can think it, in one way the pole will support the flow, in the other way it will restrict the flow. So in which way you have to simulate it? So that is what my concern.
So I didn't get your question.
So did I get my question on it? So just to go to the metal foam picture. Yeah.
Yeah.
You see it. So it will blow from the bottom, so the holes will support the flow.
That will allow the fluid to flow. Yeah.
So you will see it in the crosswise from the sideways towards the board, so it will restrict the flow.
Yeah, that will be there.
Okay.
So when there is no metal foam, fluid will easily flow.
Hmm.
So in that cases, okay, so the heat transfer enhancement will be lesser. So when we introduce this metal foam, so this will, so we can see it here. Yeah. So in the first case, if there is no metal foam, just air comes from the bottom and carries the heat from the aluminum plate. Okay. So when we introduce this metal foam, the whatever the heat that was there in the aluminum plate, that will also transfer to the metal foam. So that ligaments, whatever I have said, so from that the metal surface area increases. So here will also it will comes in interaction with that ligaments, and it will carries more heat. So if there is no metal foam, so the pumping power requirement, the resistance will be less. So
So you have kept the both sides same. For all the
means when we manufacture, that depends upon the preparation of the metal foam.
that one.
Yeah.
So for the simulation, you have kept the both sides same for everywhere.
Yeah, so porosity, what I have told, 10 ppi. So 10 means pore density, we can call it as 10 ppi, and porosity that we kept constant.
Another point is that whenever you will simulate it with smaller diameter
Yeah.
or the larger diameter ones, so the attachment with the heater, so the surface area that is getting attached to the heater, that will vary.
Yeah,
So the conduction of heat towards that foam, so that will vary.
yeah, definitely. That is what I told you. So the factors of pore density, porosity plays a major role in the heat transfer enhancement. So that by varying that one also, we can do the investigation and all those things.
My question is that, so when you are keeping it at a 25%, 50% and
Yeah.
70% one, so along with that, how this conduction part is being affected? So have you tested anyway?
Conduction part.
Means the transfer of heat from the
Yeah,
heater
yeah.
toward the
That is kind of so it is combination of both conduction as well as convection that is taking places. Yes.
so here, if you are changing the pore size, so the conduction part will be moved.
Yeah.
If you are reducing the amount of
Metal foam. Yeah, filling
so
percent.
the convection part will be moved.
Yeah.
Okay. So there might be some coordination in between these two. Means how much portion should be attached with the heater and how much flow should be there from the bottom.
See, in all the cases, the contact with this aluminum metal foam, that is same for all the cases.
Yeah, here I'm not talking about the present.
Yeah. That is fine.
He is saying that you can extend this analysis
Yeah. That is what.
so
we
that
can-
conduction and
Convection.
can be coordinated
Yes.
to find an optimum pore size.
And here you are using air.
Yes. We can use it. Miss.
So if you think it in terms of heat exchange of purpose, then that water. Or
Yes, that can also be done. So that further analysis we can.
Available with that.
Yeah, available. So we can use water also, as well as I told you nanofluids. So basic water plus along with like cuprous oxide or copper oxide, aluminum oxide, iron oxide, like that nanofluid can also be introduced. So further enhancement it is possible.
You have a plot of your grid you have used.
Yes, sir. I have considered that grid study also. Grid study. No, in this presentation I have not presented.
Question is, how do you resolve this porous structure? So you use Gambit for
Gambit, yes.
grid generator, and then you use Fluent or
Gambit, it is for machine modeling and machine purposes. I have used Gambit, and for simulation purpose I have used ANSYS Fluent. ANSYS Fluent.
and the Fluent. Yeah, so you solve the equation system for the gas phase. So how do you resolve this porous structure? Is it just an solid block with specific parameters, or do you have a fine grid and you have all the fine channels?
Solid it is there, sir. Then grid.
So when you look at Fluent, you can represent porous structures by some specific parameters. Let's say in this area, I have a porous structure
Yeah.
with this porosity, this density, this heat transfer coefficient, and so on. So you do not resolve it very fine because you're not interested what is happening inside the porous structure.
That flow is also very much important parameters, flow through porous structure. So in that also we have considered laminar, transition and turbulent
Yeah, do
regions.
you resolve this?
Yeah.
So your
So
grid also you have a very fine mesh inside your grid which represents the material.
yes sir, yes sir.
Yeah.
So we have considered that factor also. So based on the pore diameter, we have calculated the Reynolds number. So for empty channel, so as we know it, less than 2300 laminar flow transition between 2300 to 4000 and above that turbulent. So same way for porous media also. So we have calculated the Reynolds number based on the pore diameter. So in the literature it was observed that if it is less than 150, then the laminar flow it will be considered there. So if it is greater than that, turbulent flow it will be considered. So based on our cases, so we have considered.
The question I have, if you have different possibilities to use, for example, flow and for this. So your grid is here and here. Here you solve your equation system, and this is represented just by 1, 2, 3 numbers, and you have here a boundary and here a boundary. So you say the flow is coming here with a velocity of blah blah blah. Back up. And a temperature of Kelvin, and then you continue calculation here, and this path here is just represented by some parameters. Or you can resolve this also in your grid, so you have also some elements where you solve your equation system. That was my question. How are you doing this?
Yes, we have some governing equations. So
you do not resolve this.
I have not resolved that one. So
Yeah.
that the Fluent software it is there, no? So that it takes care of that one. So we have that continuity equations, momentum equations, energy equations that will be there. So that parameters.
No. Do you have grid points here inside?
No.
No, it's
No.
just represented the simple model.
Yeah.
That was my question.
Yeah.
Thank you.
To measure this temperature and all those things, we have thermocouples it is attached.
How this study is different from porous radiant burner? Porous radiant burner you have heard of? We have some radiant burners. We have conventional gas burners we have, where the mode of heat transfer is mainly convection. Radiant burner is only mode of heat transfer is only radiation. So conventional burner can be modified with a porous structure. So it is claimed that their efficiency can be enhanced.
Yes, we have to look into that.
There also porosity plays a very important role.
Yeah.
And in porous burner case, the materials are different. Ceramics.
Ceramics.
Yeah.
Yeah, that is what exactly my question is. Because in the porous radiant burner, the flame moves through the holes. Okay. So here also the air should move through the holes.
Yeah.
But here as per the structure, so it's not moving through the holes. As it is a two-dimensional analysis. That is why the restrictions are more. Air is not flowing through it. Okay. Otherwise, if it could have been a 3D analysis, then the structures are not opposed much. Okay, so it might have allowed the air to flow through those structures, through the holes. But here it is indicating that the boundaries are opposing the flow.
No, it's just a representation of that one.
He is research was something on heat transfer. Yeah, not probably.
This is there is no boundary like that. So it's just a
So
representation.
you are, so I know you are
What he
defending
is
what
asking, like let's say if you stack this holes, metal holes,
Yeah.
you stack it up. If the holes are not aligned properly in experimental application,
Yes, definitely.
if they are not aligned properly, then of course they flow and there will be more pressure.
Yeah, that is what. When we introduce the metal foam, pressure drop definitely increases.
If you could have given any streamline flow here, then it could have been more clear whether the fluid is entering into that honeycomb structure or not.
Yes, it will interest. See, this is just a representation. I have a boundary like this.
Yes.
So actually, it is like if it is a metal foam, yeah, air will flow through this one.
That is the main.
Yeah, it will flow. So just a schematic representation, I have shown it.
Yeah, no, it is flowing. What
Yeah,
you
it
said
is
that
flowing
in
through
your
this one.
Simulation, you have not made grid, na?
That's not necessary. You can represent it by specific parameters you have measured or you get from the other group.
Huh.
ठीक है, you have to think about the extension of this work in the frame of combustion, radiant burners. That becomes more effective. Second thing what he says is that ceramic materials can be. Anyway, you are here for 2 years, so you can make some proposal in this line.
Sure.
Maybe during your 2 years you can think about doing some research on this line.
Thank.
So anyway, this presentation helps you to write a proposal. You have been asking what are the topics I need to. One topic you can think of this.
Yes. Yes. Thank.